Thank you, Paul, for the kind introduction, and thank you, Jim, and to Fritz and to Marjorie and all the organizers and the staff who make this conference possible. Just wonderful to be in this community to talk about Energy 3.0, the future of energy. Hopefully we can develop things that are cost-effective, they're sustainable, they're clean. But I'm going to start with something that's rather paradoxical, and I'd like to start by talking about fossil fuels, because this is the incumbent technology. 80% of our world energy comes from fossil fuels, and I thought it would be helpful for all of us to kind of think about fossil fuels in maybe a different way than we might normally. And so I'd like to use as an example to talk about petroleum, and we can be thinking about gasoline as we discuss these properties and the attributes of fossil fuels. And first of all, let's all recognize that it is a massive worldwide resource. Okay, there are concerns, if we reach peak oil, how much will it last? But let's face the facts, 5 terawatts, okay, 5 trillion joules per second is what we're consuming right now of petroleum products worldwide. That's 1/3 roughly of the entire energy portfolio of the globe at 17 terawatts. And the other two fossil fuels of coal and natural gas, you sum that up, you get 80% of those 17 terawatts. So whether it runs out or not, great question, but my goodness, we use a lot of it. It also has a huge energy density. The energy density, even think about this, you just take your car, you could be running on fumes, okay, you stop at a gasoline station, 3 minutes later, you're fully charged up, you could drive your family to Los Angeles from here, okay, with all the luggage and all the people. I mean, you do this in 3 minutes. The amount of energy in just a typical gallon of gas, or a typical car tank of gasoline, is equivalent to 1 million gallons of water sitting 200 feet overhead. Okay, another way of thinking about it, it's 80,000 iPhone 6 batteries, right? That's just one tank of gas in a Honda Accord or a Toyota Camry. It's not only got a higher energy density, it's got a huge power density. It can power anything we could pretty much dream of, right? Automobiles, trucks, shipping vessels, commercial aircraft, military aircraft. And the power transfer of filling up your car, you're just sitting it there at the pump with your hand on the pump. If you were to convert those units of intrinsic energy going into your car, if you convert that to electricity, that would be 5 megawatts of power. Okay, a typical nuclear reactor, 1 gigawatt. That's like 200 Honda Accords, just people filling up their car at the same time. Yet it's all very chemically stable. Huge power density, huge energy density, but do we worry about our cars exploding? No, right? I mean, of course, there are famous cases where that has happened, but by and large, we've taken care of that from an engineering perspective. So they're huge energy density, huge power density, yet very chemically stable, very easy to store and transport. The United States alone has 100,000 miles of gasoline pipeline, so they refine it in Houston and ship it out to here, or ship it out to the Northeast, et cetera. Very easy to do. We do it already. And the cost, I mean, the cost, today's price is obviously across the nation around $2 to $3 per gallon. How does that compare with other commercial goods? You know, what does a bottle of water cost? How about a gallon of milk? How about a half gallon of orange juice? A half gallon of orange juice is $4, right? That's already more expensive than 1 full gallon of gas. And to me, a gallon of gas, far more valuable. As much as I enjoy the orange juice that were provided for us today, I would prefer the gallon of gasoline. Lastly, I just want to make a point about convenience. And I don't know if anyone has done this. I time myself when I go to the gas pump. I look at my clock, my watch, I start filling the car, and it never takes me more than 3 minutes to fill my car. Okay, usually it's more like 2 minutes. And to think about that, let's say your phone dies, the battery dies, and you want to plug it in. You're at an airport, you're trying to connect flights, you plug it in for 3 minutes, that's all you've got. You're lucky if you can boot up your phone after 3 minutes, okay? So you just look at all these properties, and first of all, it's like, oh my goodness, no wonder we use fossil fuels as much as we do today at this 80% clip. It's also important for us to recognize that these, any energy technology that we're interested in developing needs to compete with these attributes. And I don't know if we're going to find one technology, one new Energy 3.0 technology that's going to do all of this for us at the 80% clip, but I do think that we find the right superposition of technologies, we can sum these up and get to close to 80%. Okay, so that's one of the goals, I think, of what we're trying to do here in Energy 3.0, and I'll be talking about one piece of that puzzle. And that piece of the puzzle is about the renewable production of fuels and chemicals. Meaning the idea is, we have these wonderful properties that I showed you on the previous slide. What if we can make those same molecules in a renewable manner? So let's take a black box, typical engineering analysis. You have a black box and you feed into it 3 things that we have in abundance on Earth. We have lots of sunlight, we have lots of water, and we know we're all breathing lots of CO2. And you feed these things into the black box, and what you're asking that black box to do is to break bonds and make bonds. So you can get 2 output streams, one of which is molecular oxygen, and the other is a list of very important fuels and chemicals. These are chemicals that we already use at a massive scale today. Almost all of these are derived primarily from fossil fuels. Hydrogen, carbon monoxide, alcohols, hydrocarbons, pretty much any organic product you can think of that contains a carbon, hydrogen, and oxygen. And if you could do that, then you've got a renewable pathway to make fuels, or a renewable pathway to make chemical products, chemical products, or chemical precursors that can then be fed into the modern chemical industry to then make the product that you're after. Okay, so one of the big questions, of course, well, what's going to go inside this black box? And that's the theme of what I'll be talking about today. Now, before I jump into that, let me just say, what are you going to do if you can make these fuels renewably? Well, first of all, they're plug and play with 80% of our energy infrastructure already, so that's good to know. But some key examples of where they might really fit in is, for instance, really long-term energy storage, especially at the season time scale. If you want to store it on the order of months or years, we know that these technologies, wind and solar, are fantastic, but they are intermittent in nature. So if you could use that energy to make fuels, you could store it easily on the order of a year and make electricity whenever you need it later on. Another point is transportation. I'm a big fan of electrification for transportation. But there's a lot of transportation that is very tough to electrify. Okay? Heavy-duty trucking, shipping vessels, aircraft. Okay? Those are a lot trickier, and that's the segment of transportation that's going to grow the fastest in the coming decades. So this is another area where fuels really make a lot of sense. So what might fit inside that black box, what I'll talk about today, are two types of technologies that are based on electron-driven chemistries. So talking about grabbing renewable electrons from things like wind and solar, feeding it into a device that grabs that carbon dioxide and water and does these chemical transformations. Or you can take the same catalyst that would be composed of this electrolyzer unit and just layer them onto semiconductors, the same types of PV-grade materials that we just talked about. You can shine light on such a system and dunk it under water, feed in some CO2, do those chemical transformations in one shot to make things like methanol, hydrogen, gasoline, ethylene, whatever it is that you're interested in. Okay? So in my laboratory, certainly we're very big on developing catalysts for these chemical transformations. Any such scheme would require good catalysts. We focus a lot on making hydrogen from protons and electrons, or sticking protons and electrons onto CO2 to make organic products. For this, you need a source of protons and electrons. We like to get them, again, from water. You crack water, and you can release the protons and electrons that you need. If you read these reactions left to right, that's the fuel production direction. Again, something you'd want to couple to renewable energy like wind or solar. We're also very interested in catalyzing the backwards direction so that you can get the energy back out of the fuel as much as possible. We've been doing a lot of catalyst development, and then more recently we've been focusing more on translating these into devices. So either devices that are kind of like grid-scale storage type solutions for storing electricity in the form of chemical bonds, or putting these catalysts onto semiconductors, as I mentioned before. So you can do a direct process, shine light onto your semiconductor system, and catalyze these chemical transformations. More recently, we've also been involved in more thermal-based catalysis. Everything you're seeing up here is really electron-based chemistry. Down here, we can do the same types of chemistry, but using temperature and pressure. So we're very interested in driving these reactions of consuming carbon dioxide to make, again, fuels and chemicals in a renewable way. So my theme for the talk today, there's two segments of what I just showed you on that mosaic on the previous slide. First, I want to talk about hydrogen evolution. How do we develop catalysts for hydrogen and integrate them onto semiconductors so we can do photon-driven processes? And then I'll conclude with some thoughts on carbon dioxide reduction. How can we use electrochemical transformations to directly convert CO2 back into fuels and chemicals? So let's start with the hydrogen case. Now, I thought it might be helpful. This is a video that a collaborator of mine at the National Renewable Energy Lab sent me. This is Dr. Todd Deutsch. He's one of the leading experts in photoelectrochemical hydrogen evolution. And we're looking at a 3,5 semiconductor, a gallium indium phosphide sitting on gallium arsenide that is immersed in water. He shines light on it inside the laboratory, and you can see the bubbles coming off. So really, this is just to show you that this is not pie-in-the-sky chemistry. These types of materials really do exist. They really do happen. This really can work. Todd is so gracious as to zoom out for us and prove to us that he doesn't have a 9-volt battery driving this process. He's just simply shorted the electrodes, has one electrode making hydrogen, the other making oxygen. He also wants to prove to us that he doesn't have some fancy lamp that can do this that the sun cannot. And so he actually takes this outside. This is the sun in Golden, Colorado, which is where NREL is located. And you can see bubbles off of the same device, whether it's AM 1.5 radiation or it's simulated light. So these are the types of devices that I'll be talking about in the first segment of my talk, where we're trying to develop a way to make hydrogen renewably and sustainably directly from solar photons. So now, before I dive into those details there, you might be interested, hey, does this even have a promise in terms of the cost? So we did some studies to answer the question, is photoelectrochemical water splitting, which is what we're talking about here, is it feasible for large-scale hydrogen generation? And to that, we actually went pretty deep into the details of designing chemical plants. It's pretty much chemical engineering plant design mapped onto renewable energy technologies such as this that don't have a commercial segment just yet. And so we did a full-scale chemical plant design based on some initial reactor designs. And those of you who are chemical engineers in the audience know that you start by designing your reactor, and then you design all the auxiliary units of the plant, all the separations units and the pumps and the compressors, et cetera, to deliver purified and compressed hydrogen out the plant gate. And the whole idea is to hit this target of about $2 to $4 per gallon of gasoline equivalent. Right? And so 1 kilogram of hydrogen is about 1 gallon of gasoline equivalent. So if you can make hydrogen about $2 a kilogram or $2 per GGE, that kind of gives you a sense of, hey, that's not a bad deal if I go up to the pump and fill up my car. So what I'm showing you here are some results. This is a feasibility study. Involved a lot of folks. The lead author was my student Blaze, who kind of pulled all of this together. And you can see that we get different costs for hydrogen out the plant gate as a function of the type of reactor that was selected. So, but the good news is that while the prices might vary, they're all kind of in that ballpark, not too far from that $2 to $4 per kilogram target. Some are cheaper, some are more expensive. The cheaper ones are based on these particle designs. They're very inexpensive from a capital cost perspective, but they're not very high performance in terms of where the materials have been developed today. The panel-based systems, which look a little bit more like PVs with or without concentrators, those give higher costs, but this is where the materials really have shown the highest performance to date. But the interesting thing is these numbers are not set in, all said and done. They're based on a lot of assumptions. If we can improve things like device efficiency, going from 15% to 25%, for instance, you can get a reduction of cost from a $4 value per kilogram to $2.90. And if you can reduce the photoelectrode cost from $316 to $200, or the lifetime from 10 years to 20 years, you can see these are all cost reduction strategies. And these assumed values, nobody's made photoelectrodes that can operate with those efficiencies and stabilities and costs. But the point is, if we can do this and in a fundamental lab setting and develop the technologies to get it to a point where we can start getting close to these numbers, that tells us that we might be ready to commercialize and actually reach these types of targets of making hydrogen at around $2 per kilogram. So that's really what motivates the work. So let's talk a little bit about some of the work that we're doing in my lab on developing catalysts and surfaces and interfaces for PEC hydrogen evolution. And a lot of our work is actually inspired by nature. Platinum is well known as the best catalyst for making hydrogen. Platinum's wonderful. We don't need anything better than platinum, but we all know the issues. It's very costly, it's scarce. It'd be nice to use non-precious material instead. So look no further to some enzymes that Mother Nature has cooked up for us. Hydrogenase and nitrogenase are just a couple of the varieties. No precious metals whatsoever, yet they're known to operate just as efficiently as platinum for this reaction. So this is some work from theory done by Jens Nørskov, who at the time was a professor at the Technical University of Denmark. He's actually here on the faculty, and my colleague at chemical engineering at Stanford. He and a postdoc, Berit Hinneman, did some studies of the active sites of these enzymes and figured out what makes them tick. And it turns out that these sulfur groups at these edges turn out to be the moiety that does the chemistry in the enzyme according to their theory, which really pointed them in the direction of, hey, is there a solid state material that might resemble this type of motif? And in fact, the edges of molybdenum sulfide showed that they had a kind of similar structure of a twofold coordination, similar to the sulfur that you see here. Now, this is interesting. They predicted this is a very good catalyst, but it's funny because at the time there was 20 years, 30 years of literature saying molybdenum sulfide is a terrible catalyst for hydrogen evolution. Turns out that all that work had been done on bulk materials with not a lot of these edges. And so when I was a postdoc at the Technical University of Denmark, we went about synthesizing these really small nano triangles of a few nanometers each that expose lots and lots of edge sites. We did the STM imaging to see at the atomic scale what the surface structure was like. And then we pulled these out of vacuum. And not only did we see that they're actually very good catalysts, I don't want to dive into that data just yet, but we found that the catalytic activity did not scale with the surface area of the molybdenum sulfide. It scaled with the edge length of the molybdenum sulfide. So it was really conclusive experiments that really said that the theory was right and the edges should be good. This motivated a lot of the work when I started my group at Stanford. We went about synthesizing lots of different nanomaterials of molybdenum sulfide, thin films and nanowires and nanoporous materials and molecular clusters, all in the spirit of trying to get as many edge sites as possible because we knew that that's where the action was happening catalytically. So one example I want to show you is these core shell nanowires. This is work that was led by my PhD student, Jabot. And he had these nanowires, these core shell nanowires, which he fabricated, which have a molybdenum oxide core and a molybdenum sulfide shell. And this molybdenum sulfide shell, you see the molybdenum sulfide structure is actually very similar to graphite. It's got this layered structure. And it's very thin. It's only 2 to 3 nanometers thin. And so these core shell nanowires, we can look at this plot as a plot of activity, Where we want to be where platinum is, you can see that this is current versus voltage. Platinum gives you an awful lot of current for a very small penalty in voltage. You only have to put in a few millivolts on platinum. You can drive hydrogen quite well. The non-precious materials here require more like half a volt to drive the reaction quickly. The molybdenum sulfide is somewhere in between. Not quite as good as the precious metals, but certainly better than a lot of these non-precious metal materials. So that was exciting. This is an active catalyst for hydrogen evolution, but what I actually thought was even more intriguing was the stability. We showed that in sulfuric acid, Jabot came up with a really punishing accelerated durability test where he did 10,000 cyclic voltammograms going positive, negative, all the meanwhile measuring how much potential, how many millivolts do I need to provide this thing to give me 10 milliamps per square centimeter of current, and lower would be better. And the good news is that, well, first of all, it only required about 1/4 of a volt all the way through. That's a pretty small penalty to pay, especially for a non-precious metal material. But as you can see, this data is totally flat. So it's just as good at the end of the experiment and arguably a little bit better at the end than it was at the beginning. So it's not only very active and non-precious, it's also very stable, all in a very corrosive electrolyte. So we went about with this kind of confident outlook of, well, if molybdenum sulfide can protect molybdenum oxide, which is completely unstable in sulfuric acid, maybe we can protect anything. So we went about testing this with silicon. So my PhD student, Jesse Bank, went about synthesizing, using some of the exact same fabrication techniques that we just heard about on the crystalline silicon world, basically making a PN junction and then putting a very thin layer of molybdenum down and then sulfidizing it to make an MOS2. The idea of making a photoelectrode where the silicon is doing the light absorption charge separation just like a photovoltaic would, but then sending those electrons into the molybdenum sulfide to then do the catalysis in water. And so here's some cross-sectional images of this device. I'll zoom in a little bit further. This is work in collaboration with Bob Sinclair in materials science. And you can see the single crystal nature of the silicon photovoltaic underneath. This is a molybdenum silicide layer that forms intrinsically when you deposit molybdenum onto silicon. Here's a molybdenum metal layer, and then at the top we see the sheet-like structure of MOS2. So we fabbed what we hoped we had fabbed. The question is, how did it perform? So we then encapsulated this in an epoxy, immersed in a sulfuric acid electrolyte, again 0.5 molar, and we shined AM 1.5 radiation. What did we find? Well, we found that it was a very efficient photoelectrode for water splitting, as well as stable. So you're looking at current voltage data. Again, here's current and here's voltage. And I want to point out this 0, this is the equilibrium potential for the reaction, which means if I grab an electrode and just stick it in water and hold it at 0 volts, the backwards and forwards reaction should go exactly the same pace. Normally, you'd have to tilt an electrode to the left or to the negative side to favor hydrogen evolution. But because we're shining light onto the silicon, it's exciting these electrons, and we're using those excited electrons to drive the chemistry, we can actually get it to the right of 0, which means we're kind of getting energy out of the process, which is exactly the goal. So we're evolving hydrogen at a rate, here's our 10 milliamps per square centimeter, we're getting 0.16 volts out of this device, so to speak, to drive this chemistry at 10 milliamps per square centimeter, and you can see that at times t equals 0, at times t equals 100 hours of illumination, it's exactly the same. So very active, very stable in sulfuric acid. But we knew we could do better, and we knew that because when you look at this cross-sectional TEM image, you'll notice that these planes of MOS2 are very flat. There's not a lot of edge sites, and I just mentioned a few minutes ago that's where all the hydrogen catalysis happens. So we said, well, can we improve upon this? How can we get more edge sites? So this is where we went about making all these different morphologies, taking this knowledge from the core shell structures, and then making nanoporous materials, and more recently these molybdenum sulfide clusters. These are molecular clusters, MO3S13, just chock full of edge sites. And the trend on this particular plot is that as you engineer more and more edge sites into your molybdenum sulfide, you get more and more activity. So we took this catalyst, which was the best of the bunch. We just made an ink out of it. Okay, so we synthesized these clusters, a pretty simple wet chemical synthesis, and then we literally just sprayed it down on top of that device that I was showing you before, okay, using just a spray painter from a hobby shop. And what we find is that we can actually improve the activity. We can actually shift it about 110 millivolts to the right. And now we're getting 10 milliamps per square centimeter, which is keeping up with our solar photon flux at 0.27 volts versus the reversible hydrogen electrode. Okay, so we're getting 0.27 volts out of our device while we're keeping up with the solar photon flux. Can we do even better? So now we've been transitioning. The molybdenum sulfides is a great family of materials. And for a lot of the reasons that the molybdenum sulfides work, actually it turns out that metal phosphides can work as well. This is work from my PhD student Tommy Helstern, who's in the room. He's presenting a poster on this later. And these are some cobalt phosphide catalysts that he's been developing. When he layers them on top of silicon, runs this in sulfuric acid, you'll see he's reaching this 10 milliamps per square centimeter now at positive 0.35 volts versus reversible hydrogen. So we can put all of these plots together, and I can show you on one single current voltage curve. This is the original MOS2 on silicon. This is when we add this MO3S13 catalyst, and now this is the cobalt phosphide catalyst. All the meanwhile, we're basically marching to the right, which is the direction we want to go. And our goal is really to get to this point here. This is platinum on silicon. Again, platinum is as good as it gets, but of course it's a precious metal. Our goal is, can we fulfill this gap and make non-precious metals that can actually reach or maybe even exceed that of platinum? So this is what you're seeing here in green. This is the most active silicon photocathode that has ever been reported using non-precious metal materials. Now with my last bit of my talk, let me switch gears to a different reaction entirely, which is carbon dioxide reduction. I want to tell you a little bit about what we've learned on transition metal surfaces. So it's a great place to start when you're looking at any reaction. Let's talk about some thermodynamics and kinetics for a moment. I'm plotting you here a number of different reactions involving CO2, taking it to CO or to methane or to ethylene or to alcohols, right? Some very nice, valuable products here. And from a thermodynamic perspective, I just want to point out these numbers. These numbers are the equilibrium potentials for these different reactions, which is an electrochemist lingo for thermodynamics. It's another way of looking at delta G. And the point I want to make here is that all of these numbers, you don't need to be an electrochemist to see that all these numbers are very similar to 0, which is the same, which is the number that's relevant for the hydrogen reaction. Which really, stated another way, if you give me electrons that are energetic enough to go into protons to make H2, those electrons are every bit as energetic enough to go into carbon dioxide to make all these really nice products. So the overall thermodynamics for any of these reactions are almost identical. The challenge, though, is the kinetics. All of these reactions are much, much tougher to catalyze than hydrogen. And to explain that, let me take a look at the methane example. If you want to go from CO2 to methane, you need to stick 8 protons and 8 electrons onto CO2 to get there. So let me invoke some simulations from Andy Peterson and Jens Narsko, where they looked at, and others, who looked at CO2 impinging onto a copper surface. So imagine that first proton and electron gets transferred. You make a carboxy group, COOH. Another proton and electron gets transferred. You hit this OH to make water. Now you're left with the carbon monoxide behind on the surface. You hit that with the H plus and an electron, you make HCO. Then you hit it again, you make formaldehyde. You hit it again, you make methoxy. Notice that this methoxy is standing straight up. So if you were to hit this oxygen down low with your next proton and electron, you make methanol. If you hit this methyl group up top, you make methane. And I said, let's look at the methane example. So you hit this one up top, we make your methane, you have an oxygen just blocking your surface, so you better clear that. You're going to clear that with 2 more protons, 2 more electrons to make water. Voila, you've got a clean surface, and you go all the way back to square one. Point being, my goodness, that felt tedious just talking about all of that. Imagine asking your catalyst to do all that for you, and to do this, many times per second, hundreds of times per second, ideally. So it's an awful lot to ask of your catalyst surface, and the problem is that for a catalyst to work well for this overall reaction, it has to work well for every single step of the reaction. We all know the concept of rate determining step. One of these steps is bad, it kills the whole system. So that's really the big trick, is how do you design a catalyst that is active for all of these steps and efficient for all these steps, and that is selective to make the product that you want and not the products that you don't want. So to explore all of this chemistry, we developed some new methods to study this reaction. I don't want to go into all the details, but we did some electrochemical reactor engineering to design a reactor that we thought would be helpful, because it was really designed to be sensitive to identify and quantify products of reaction. So I want to tell you about what we learned using this reactor, applying it to 7 different transition metals. So we applied it to copper first. This was some work from my first PhD student to join this project, which is Kendra Kuhl. And we saw something really interesting. Copper could make all 16 of these products from carbon dioxide, all at room temperature and room pressure. Okay, if you look at this list, it's a really fantastic list of different products from the smaller molecules like carbon monoxide and formate, methanol, methane, which are some C1s. You can make lots of different carbon-2 products, for instance, glycolaldehyde, ethylene glycol, ethylene, and ethanol. We made a lot of C3 compounds, things like acetone, propionaldehyde, 1-propanol. Okay, if you think about it, propanol is really interesting, right? You're grabbing 3 CO2 molecules, linking them together, pumping 18 protons, 18 electrons, all at room temperature, room pressure. Okay, so it's really intriguing what copper can do. The problem is that it really does all of them at the same time. And that's kind of tricky. Then you have a separations problem to deal with, and that's really not commercially viable. So we'd like to come up with catalysts that can make any one of these products and make it very targeted, very focused without making the rest. But having said that, it's really great that copper can do all this. And I also want to point out that 6 of these on the list are amongst the most largest volume chemicals that are produced in the globe. They're produced on the order of billions of kilograms a year production. And I love that unit in science, billions of kilograms a year, because there's 7 billion people on the face of the earth. So everything I've circled here means that every man, woman, and child on earth, on average, is responsible for 1 kilogram a year of production. It gives us a sense of scale. If we can make these things renewably, we can actually put a dent into the energy problem. So we didn't just see that these things emerged off the electrode surface, we were also able to quantify their reaction rates. And so again, I don't want to go through all these details. We mapped as a function of applied voltage how much of each product that we're making of these 16 different products. And we took all this data and ultimately were able to use it to do something that others couldn't do beforehand, and that is to come up with some mechanistic possibilities, some pathways that other people couldn't think of or dream of because they didn't have this more complete set of data. So it's really helping us understand what are the problems and the bottlenecks in this reaction, how do you develop a catalyst that overcomes them. But rather than go into all these details of these different mechanistic aspects, what I'd like to do on my last couple of minutes is just say a few words about what about other transition metals other than copper. So this has invoked a very big team effort for the work I'm going to show you right now. And that is, let's take again a look at these 7 different transition metals. And I just want to use some check marks here to give you a sense of what products are being made on these 7 electrode surfaces, whether it's hydrogen or carbon monoxide or formate or methane or methanol or C2s. And the black check marks here indicate what we saw as the major products emerging off of these electrode surfaces. And that's frankly exactly what was seen in literature beforehand. In green check marks, we detected all of these products on these different electrode surfaces. And that's exactly what people had seen beforehand. But what was interesting is because we had developed these methods to be sensitive to really identify and quantify these products of reaction, these are the ones that we had seen that no one else had seen beforehand in the blue check marks. And if I go backwards and forwards one more time, you'll see that, my goodness, it's all of these transition metals turns out can make either methane or methanol or both. And that was unknown previously. But again, we didn't just see these things emerge off the surface. We could actually measure the turnover frequencies and the reaction rates as a function of applied potential, which taught us a lot. So I'm showing you all these 7 metals and which ones make methane and how much as a function of potential, which ones make methanol and how much as a function of potential. And the big point I want to make here is that there's a strong correlation between the top panel and the bottom panel. In other words, here's nickel in orange. When nickel is making methane, nickel is making methanol. And here's zinc in green. When zinc is making methane, zinc is making methanol. And here's silver in red. When silver is making methane, silver is making methanol. So it's really telling us that there's a coupling between the mechanisms on the pathway to make methane and methanol, which is kind of good news if you want to have a nice crisp understanding of what's going on the surface, but it's bad news if you want to engineer a catalyst that favors one versus the other. It tells you you're going to have a selectivity problem. You really have to think deeply about how you're going to steer the chemistry towards one or the other selectively. Having said all this, we took all of this data and we were able to construct some plots that really elucidate some of the trends of what we've learned. So here's trends in the carbon dioxide reduction reaction amongst these 7 different transition metals. What I'm plotting for you here, this is what we call the onset potential. So what's the earliest voltage at which we see these products emerge? And I'm plotting it for you as a function of how strongly carbon monoxide is bound to the surface. We think that's actually a very important figure of merit in this reaction. And so what you see is that there's a volcano-type shape with gold near the top, meaning it's the most active for the CO2 reduction reactions. If you bind CO tighter than gold, it gets worse. If you bind CO weaker than gold, it gets worse. But it's not just about, in this case in black, I'm showing you the CO2 reduction to any possible product. And it turns out that for a lot of these metals, carbon monoxide is the primary product. But you might be interested in rather than making carbon monoxide from your CO2, you might be interested in making something more like methanol or methane. And this is what the data looks like here in red. We don't see a volcano-type curve. We see more of a plateau or a mesa. And we think we understand what's going on here. So it's interesting. If you bind carbon monoxide anywhere in this region, it turns out that it's totally flat. All these electrodes behave about the same to make methane or methanol or both. And then it has a steep drop-off for these metals. What's going on? So we think what's happening on the left-hand side, we think that all these metals are limited by the one particular step in the mechanism that I mentioned before of carbon monoxide going to CHO or COH. So we think that basically you can tune the binding energy of carbon monoxide all you want on your catalyst, but you're just going to tune the CHO binding energy exactly the same way, and you end up with no gain if it's a monometallic catalyst like this one. These catalysts on this side have exactly the same problem, but they have a worse problem that turns out to make it even worse of a catalyst. The CO here just desorbs. It pops off the surface. So you can go from carbon dioxide to carbon monoxide, but it'll just pop off the surface before you have a chance to attack it further and make something like methanol or methane. So having said all this, what we've really uncovered here, I believe, is an important design principle for a catalyst for if you want to convert carbon dioxide into products like alcohols and hydrocarbons, you really need to get through this carbon monoxide intermediate. Going from CO2 to CO, no problem at all. But if you want to go down to these more longer chain products or larger products, maybe perhaps more valuable products, we need to get through this step. And this is something we're working in concert with Jens Norsko and his team on theory, who've come up with some schemes on how to attack that problem. So this is the latest phase of the research, is taking that knowledge from theory and incorporating it into catalyst design. So let me conclude with some major points. First of all, I do believe that renewable fuels are feasible. The techno-economics are showing that it could potentially be possible, but we have to develop better materials to get there. So a lot of work needs to be done between now and then. I showed you some of our work on developing non-precious metal hydrogen catalysts, as well as developing acid-stable photocathodes for hydrogen evolution. And we're uncovering these very important design principles that are going to tell us how to tackle a very tough chemical reaction, which is electrochemically converting CO2 into fuels and chemicals. So with that, let me thank GCEP is one of our primary funders for the work that I showed you today, an EFRC that's funded by DOE known as SNEAK, the Office of Energy Efficiency and Renewable Energy at DOE, as well as the National Science Foundation, and many students and postdocs that I was kind of naming along the way who are participating in this project. In particular, I have two students in the room, Jeremy Feaster and Tommy Hellstern, again, who are going to be presenting posters, Jeremy on CO2, Tommy on hydrogen and photoelectrochemistry. So please see their poster and ask them lots of questions, and I'd be happy to take any questions as well. So thank you very much. Hey, Jim. Thank you.
So we have time for a few questions.
Excuse me.
Thank you. Very interesting talk. Doug Rose from SunPower. With PV costs producing electricity now in some parts of the world at 5 cents a kilowatt hour without subsidies, there's a lot of interest now in combining that with Fischer-Tropsch process and really cheap gas to make jet fuel. Do you see this work as complementary that, feeding that methanol, or do you see this as eventually being able to bypass that whole product and go to something even cheaper?
Wonderful question. Yeah, the answer is that I think we want to be as flexible as possible. So we've got two extremes. We've got the conventional processes, conventional Fischer-Tropsch, where you grab something like coal, you gasify it to make your carbon monoxide, you have hydrogen coming either from the coal or from natural gas, you blend these streams together, all temperature pressure processes to make fuels. Okay, that exists today and at large scale. We know how to build those plants. Another extreme is a purely electrochemical process where you're doing all of this electrochemically. And there's distinct advantages and disadvantages depending on where you go. We can talk about that. One advantage of the purely electrochemical case is it becomes more modular because it's room temperature, atmospheric pressure. You can make small units. You can put it out in remote locations. You don't need a multi-billion-dollar chemical plant to do it. You can go down to the 100-watt scale or a kilowatt scale if you wanted to. Now, having said that, so there might be different niches where that would make sense. Combining them could also make a lot of sense. So you could have more combining conventional temperature pressure-driven processes with electrochemical processes that kind of feed in the right starting point. So for instance, maybe we do just ask our catalyst to stop at CO. You don't need to go all the way down to methanol or gasoline or ethylene. Just stop at CO and provide that CO instead of getting it from coal. And then now you have to answer the question, where's your hydrogen going to come from? Okay, that in principle could come from an electrolyzer unit as well that feeds into a temperature pressure process, or maybe that comes from natural gas, which is the conventional way that the hydrogen is made. So I think there's a lot of room in between. There's a gradient. I think of it as kind of a gradient in how renewable does your renewable fuel need to be. And for the short term, I think we want to for sure keep all of these options open, explore them. And I think what might be great for the short term, we could maybe advance to have a better solution in the midterm, and in the long term, make it as sustainable as possible. Yes?
So Mike Schumay from Baker Hughes. A very, very interesting discussion. I really appreciate this.
Thank you.
One of the, I was waiting for you to talk about a little bit more on the some of the processes that was developed by nature, and that's basically what you're doing is that you're capturing the light by means of a path of electrons that goes through certain metals and facilitate
That's right.
Capturing the energy. Well, photosynthesis has developed this throughout a series of enzymes and coenzymes. I'm just wondering that is your research involve some of the work, some of the processes that has been developed by nature, and trying to see if we can mimic some of that, because that's generally probably is the most efficient way of doing this.
Absolutely, absolutely, and there's no question. And this is some of my, if I think my broader view of catalysis is kind of the situation the way it is today. If you say the word catalysis to somebody, it means different things to different people.
Right.
People who work more in the biological side of sciences,
Exactly.
the first thing they think of is an enzyme.
Right.
You ask a ultra high vacuum surface scientist, they'll think of rhodium 109.
Right.
And there's a lot of room in between. And so I think it's very important for the catalysis community. I mean, at the end of the day, you're just breaking bonds and making bonds.
That's right.
I don't want to trivialize how challenging that is, but we can learn so much from the different communities. So absolutely, we pay attention to the biological literature. There's lots of enzymes that reduce carbon dioxide.
Right.
They make either CO or formate. So we're trying to understand how those work. The typical photosynthesis construct, unfortunately, is not really designed to make fuels. It's designed to make sugars, right? It's attaching a carbon onto a five carbon and to make a 6 carbon sugar.
Right.
And that's all fine and good, and we can burn that as biomass and
Right.
get, there's another scheme for the black box.
Right.
But in our world, right, so we're kind of focusing more on the solid state type of devices, but we absolutely are learning as much as we can from nature. One of the tricky things is that nature is obviously such a complex macromolecule and how it does its thing. We're getting more and more definition as to how that works, but we can only learn as much as that community is providing in terms of the insights on the inner functions. So that as that advances, we can advance our understanding on how to put those design principles into a solid state system.
Sure. It was just striking to me to see that when you put that path of reactions that goes, electrons go from one to another, and you're producing that there is a path in in these type of natural processes that electron travels, and just learning why it's going through that process is very important for the catalysis.
I think the most important thing that I've learned from an enzyme is that an enzyme has 2 features that are really tough to mimic in a solid state material. Number one is a three-dimensional type of site,
Right.
As opposed to a lot of what I was showing you today. These are kind of flat 2-dimensional surfaces. So it basically has different points of attack to
Right.
grab onto molecules and twist and turn them around
Exactly.
to break the bonds. The second thing is it's really flexible. It's a very flexible system that as soon as it accepts a molecule, it will change its own conformation, its electronic structure changes. It's very dynamic.
Right.
And not to say that solid state materials, I mean, nanoparticles can be dynamic too, but they're just not nearly as dynamic.
Yes, yes.
So that's where I'm thinking is how do I design a solid state material to have some of those elements of the flexibility, the three-dimensionality, the adaptability to the reaction pathway. I think those are wonderful things to build in.
Right.